In this module, we are going to review matrices. We'll define matrices. We're going to define operations such as transposes, inverses. We're going to talk about linear functions and how they are related to matrices. We're going to define concepts such as rank, which will play a role later on in the course in defining complete markets and hedging instruments. To start at the very basic, what is a matrix? A matrix is simply a rectangular array of real numbers. And we represent a matrix by the number of rows and the number of columns. So I'll walk you through some examples. So this matrix A has two rows, row 1, row 2. It has three columns, 1, 2, and 3. And therefore, we're going to call it a 2 by 3 matrix. 2 rows, 3 columns, 2 by 3 matrix. Its elements I'm going to index by the row index and the column index. So if I'm talking about an element called A1, 2, so the first index is going to be the row index. The second index is going to be the column index. So it's going to be row 1, column 2. So that's the number that I'm talking about. So A1, 2 is equal to 3. Similarly, if I talked about another element A2, 3, so remember the first index will refer to the row. So we're talking about the second row. The second index is going to refer to the column, the third column. So that's this element down here. So A23 is equal to 5. So every matrix is a rectangular array. We say a matrix is an M by N matrix if it has M rows and N columns. So that's down here. So this is the general A that I'm talking about. This particular matrix has M rows. So if you look at a particular elements over here, it goes from A11, and remember the row index always comes first. So it's A11, A21, and so on. These dot, dot, dot means and so on. AM1. It has N columns. So the column index comes second. So it's A11, A12, A13, and so on, and A1N. And the last one is AMN. Here's another example. B, it has 1 row and 3 columns. That's a row vector. In the module on vectors, we noticed that there were two kinds of vectors. So column vectors and row vectors. Row vectors have row equal to 1 and a many number of columns. Column vectors have column equal to 1 and several rows. So here's an example of a column vector. W equals 3, 4, 1. 3 rows, 1 column. So either I can think of it either as a vector in R3 or as a matrix in R3 times 1. The second one says it's got 1 column and 3 rows. So the first thing that I want to do is introduce an operation called transpose. Transpose really takes rows to columns and columns to rows. So the easiest way to start thinking about it is to think in terms of column vectors and row vectors. I've got a column vector here, V. It's got 1 column and 3 rows, 1, 2, 3 rows. If I take its transpose, if I put the operation transpose on this vector V, I'll go from column to row. So V transpose is simply this row vector. Now we want to do the same thing to matrices. I want to pretend that the matrix is nothing but a collection of columns. I'll take every column and flip it and make it into a row. And that's what a transpose does. I have a column 2, 1 over here. I'm going to flip it and make it a row, 2, 1. Same thing that I did with the vector. I had 2, 6, 4, 2, 6, 4, 2, 1, 2, 1. I take the second column and I flip it. I get the second row. I take the third column and I flip it. I get the third row. So columns goes to rows and vice versa. Rows go to columns. It's symmetric in that sense. More generally, here's a matrix A, which is Rm times D. To remind you once more, M is the row index, D is the column index. So it has M rows and D columns. If I put the transpose operator, that's what this is doing. I'm going to take this column and transform it into a row. And that's what I'm going to do to every one of them. So now, after the transposition is done, you end up getting that the number of columns becomes the number of rows, and number of rows becomes the number of columns. And so a matrix which is in Rn times D ends up being a matrix in Rd times M. In the module on vectors, we had learned that the inner product between two vectors involves a transpose and a multiplication. So we figured out the transpose part. It's going to take a column vector into a row vector. Now we're going to try to see what happens. How do I multiply matrices? So the next concept is that of a matrix. So I have a matrix which is Rm times D. So it's the row index is M. The column index, I'm going to put them in red just to emphasize the fact. The column index here is D. The row index for the matrix B that I'm going to multiply to it must be the same as the column index of A. The inner multiplication dimension should be the same. Otherwise, you cannot multiply these matrices. And the column index of B could be anything, say P in this particular case. So when you multiply these matrices, you get a new matrix. So the inner index that was there, this D index, it disappears. And the new matrix C that you end up getting is going to be in M times P. So M is the row index, becomes the row index here. And P, which is the column index, becomes a column index there. So you end up getting a matrix which is in Rm times P. The inner dimensions have to be the same in order for the multiplication to happen. And when the multiplication happens, that disappears. There's a general formula for how to get the elements of C. But before going there, let me give you some examples so that this idea becomes clearer. So I've got two matrices down here. I've got this matrix which is in R 2 times 3. 2 rows, 3 columns. This is a vector, but I'm going to treat it as a matrix which is in R 3 times 1. 3 rows and 1 column. Now, if I apply the general rule that I just talked about, I should end up getting a matrix which should be R 2 times 1, because I end up getting that the inner dimension, which is the same for the matrix A and the matrix B, that will disappear, and then the outer dimensions are what are going to define the product. So this is the matrix C that I'm going to get. That's in R 2 times 1, as I expected. So how do I get the elements of this matrix C? What I do is I take the rows and multiply them to the corresponding columns. So in order to get C1, 1, so I have, this is the row index, this is the column index. In order to get this element C1, 1, I'm going to take the first row of A and multiply it to the first column of B. I've got the first row, I've got the first column, and what does it mean to multiply a row and a column? I multiply them component by component and add them up, sum product. So I take the 2, multiply it to that 2, I take the 3, multiply it to 6, take the 7, multiply it to 4. And that's what I've written up here. 2 times 2 plus 3 times 6 plus 7 times 4. In order to make it clear what I'm trying to do here, the elements in the brackets correspond to the column, the elements outside the bracket corresponds to the row. And the first component ends up being 50. So let's look at C21, second row, first column, same story. So I've got the second row here, and that's going to multiply the same column. And I'll get elements 1 times 2, 1 times 2, 6 times 6, and 5 times 4. And if you multiply all of them together, you get 58. And that's how matrix multiplication works. So let's now go back and look at the more general case. I've got matrix A, which is Rm times D. I've got a matrix B, which is Rd times P. The inner dimension disappears. I get a matrix C, which is Rm times P. If I'm looking at a particular element Cij, this is the row index, that's the column index. How do I get this element? I take the ith row of A and multiply it to the jth column of B. So the ith row of A is AI1, AI2. The row index remains the same all the way through. Over here I have B1j, B2j up through BDJ. So these last indices actually should be D, not N. If you multiply them together using the rule that we just generated, I'm going to multiply this element with that element and component wise, and then add it up. You'll end up get this is the same as the sum over L going from 1 through D, AIL, BLD, which is exactly what we have done down here. So once we know how to multiply matrices, I can start simplifying a lot of things. L2 norm. Remember, in the module on vectors, we talked about L2 norm. We had said that L2 norm is the sum of the components squared square root. We'd already shown that this is nothing but the dot product square root. Now I'm going to show you a different interpretation for it. So I've got a vector 1 and minus 2. Its L2 norm is 1 squared plus minus 2 squared square root. I'm going to write that as 1 minus 2, that's a row vector, times 1 minus 2, which is a column vector. And why can I do that? Because if I write out the expression for what this multiplication means, it's the first component times the first component, second component times the second component, square root. So that's 1 squared plus minus 2 squared. The same thing as down here. Now this row vector, I can also write it as this vector 1 minus 2, which is a column vector transpose. A transpose takes it to a row. Now we have the same vector, a vector 1 minus 2 transpose times itself, square root. And that's what it's written down here. The inner product between two vectors is nothing but take the first vector, take its transpose, and multiply it to the second vector. Just as a reminder, we had said in the module for vectors that if I don't specify it, every vector is a column vector. So W is a column vector, V by itself was a column vector. I take its transpose, I get a row vector. Row vectors times a column vector always gives me a real number. And that's why the inner product turns out to be the real number. All right. We know what our matrix is now. They're rectangular arrays of numbers. We know how to take its transpose. We know how to take its multiplication. Now we want to take a next step and try to figure out what can matrices do. How are matrices and vectors connected to each other? And the connection turns out to be coming from linear functions. So that's our next component of this module, linear functions. I'm going to call a function linear if it has the following property. I take a vector x, I take a vector y. I multiply this vector by a number alpha, and I multiply the vector y with the number beta. Beta and alpha are real numbers. Back in the module on vectors, we had talked about that alpha x plus beta y is another vector. All we do is multiply every component of x by alpha, every component of y by beta, and add them both component by component. So now, alpha x plus beta y is a new vector. I'm going to take the function at this new vector. If it so turns out that for any choice of x, any choice of y, any choice of alpha and beta, the function evaluated at this combination vector is nothing but the same combination of evaluations at x and y. So what's important in terms of linearity is that in one case I am taking the linear combination inside the bracket. In the other case, I'm taking the linear combination outside the bracket, and the two answers are the same. Alpha x plus beta y, the function evaluated at this vector, is nothing but the function evaluated at the vector x multiplied by alpha plus the function evaluated at the vector y multiplied by beta. If this is true for all x, y, alpha, beta, the function is linear. There's a simple theorem, we won't get into it, that a function is linear if and only if I can write that function as the multiplication of the vector by a matrix. So f of x is a linear function if and only if I can find some matrix A such that f of x is nothing but A times x. It's just a multiplication by a matrix A. And that's why this is the next component to understanding what matrices can do. So if I want to have a linear function from R3 to R, I have to take vectors in R3 and I have to get a number in R. So what should be A? So this multiplication, if A is going to be in M times D and X is going to be in RD, A times X is going to be a vector in R to the M. Now I want to map R3 to R, and therefore the row index of A should be 1. And the column index should be exactly equal to D. In effect, this should be a row vector. So here's a particular row vector 2, 3, 4, just as an example. If you look at the combination, if you look at the multiplication of 2, 3, 4 to the vector x1, x2, x3, you end up getting 2x1 plus 3x2 plus 4x3. It takes vectors and maps it to real numbers. Take it one step further, here's another matrix A. Now this matrix has 2 rows and 3 columns. It's going to multiply a vector with 3 rows, and you'll end up getting another vector which has 2 components. Why 2? Because the row index is 2. So again, component by component multiplication, 2 times x1 plus 3 times x2 plus 4 times x3, that gives you the first component. 1 times x1, 0 times x2, 2 times x3, that gives you the second component. And that's what linear functions are. Linear functions take vectors, multiply them by a matrix, and give another vector. So in most of this course, we won't really be interested in just functions. We'll be interested in constraints. We'll be interested in sets of vectors that are defined by functions. These might be portfolios, these might be values of options, these might be other kinds of things that are random variables and so on. So we're going to talk about two different kinds of constraints. A linear equality. It would mean all those vectors x such that they satisfy some linear equality. This is a linear function. It's equal to some given vector b. We'll all talk about linear inequalities, which means that all vectors x such that ax is less than equal to b. When I mean less than here, I mean component by component. So I'm going to say a vector 2, 3 is less than equal to a vector 4, 5. Because component by component, 2 is less than 4, 3 is less than 5. But the same vector 2, 3 is not less than equal to the vector 4, 1. Why? Because the first component is less than 4, but the second component is not. So therefore, this vector is not less than 4, 1, but this vector 2, 3 is less than 4, 5. So if I say a vector ax, meaning the vector obtained by multiplying a to x is less than equal to b, I mean that the component by component that vector should be less than b. Why did I only show you one inequality? Because if you had an inequality which is going the other way, ax greater than equal to b, that's nothing but minus ax less than equal to minus b. So without loss of generality, I can just look at one side of the inequality. It turns out that it becomes easier to keep track of various things if I just look at one side of the inequalities. All right, I've got linear functions. I've got the notion of linear constraints. Now the next concept that I want to know about matrices is what can linear functions do? How complicated a set can linear functions generate? And that's going to be important when we start talking about spans of matrices and how we can think in terms of what these spans do. So the next concept that we're going to learn is that of a rank of a matrix. There are two notions, a column rank of a matrix and a row rank of a matrix. Let's look through the examples and then we'll come back and look at more general ideas. And another related concept to rank is the range of a matrix, and we'll try to make all of this clear by looking at an example. So down here is an example. I've got a matrix A, which is a 2 by 3 matrix. 2 rows, 3 columns. We know that this matrix induces a linear function. And what that linear function does is it takes a vector x, which is in R3. So x is in R3, meaning it has 3 components. If you multiply this vector by the matrix A, you end up getting a vector ax, which is in R2. So it maps 3-dimensional vectors into 2-dimensional vectors. This concept is important when we talk about ranges. But before we get there, let's start talking about a column rank. Column rank, I want to look at the columns of this matrix and ask myself, how many linearly independent columns are there? How many columns can I take and write and still leave them linearly independent? So I know for a fact that because the columns are 2-dimensional, meaning that each column is in R2, I can at most get 2 vectors. Back in the module for vectors, we had talked about linear independence, and we said that in R2, 2 vectors can be linearly independent, and a third vector will become linearly dependent. So at most, I can get 2 columns that are linearly independent. But it turns out that for this particular matrix, only one column is linearly independent. Why? Because if I take the first column, 1, 2, I can get the second column simply by multiplying the first column by 2. I can get the third column by simply multiplying the first column by 3. So the second and the third column are not linearly independent of the first column. So the column rank, which is the number of linearly independent columns, is 1, because I can only get 1 column. Now let's do the same thing for the rows. And we end up getting a concept of a row rank. So here's my row 1. Now it turns out that if I take that row and multiply it by 2, I get the second row. So the row rank is also equal to 1. That's not a coincidence. There's a theorem which says that the row rank and the column rank are equal always for any matrix. So it turns out that for this matrix, the row rank is equal to 1, the column rank is equal to 1, and the rank itself is just equal to 1. So next, let's look at this notion of range. So what we want to do is we want to understand what does this matrix A do to the vectors in R3. So now I want to think of this matrix, not really as a matrix, but as a function. So it's taking vectors in R3 and mapping them into vectors in R2. What kind of vectors can I get? What is the largest set of vectors that I can generate by this transformation? So I'm going to multiply them by different components. So the vector AX is going to be equal to x1 plus 2 times x2 plus 3 times x3. The second component is going to be equal to 2 times x1 plus 4 times x2 plus 6 times x3. That is what this vector AX3 is going to be. So x1 plus 2 times x2 plus 3 times x3 times 1 gives me the first component. x1 plus 2 times x2 plus 3 times x3 times 2 gives me the second component. So every vector that I can generate by multiplying by the vector x is of the form some real number, let's just call it lambda, times the vector 1, 2. And that's exactly what is written down here. The range of A, the set of all vectors that I can generate by multiplying to the right hand side of A by some vector x, is all the vectors of the form lambda times 1, 2. What does that mean? Now, going back to the notion, R2 is this plane. 1, 2, so the second component is equal to 2, the first component is equal to 1. That's this vector 1, 2. In the R2 plane, all the vectors that are possible are represented by this R2 plane. But this matrix A can only generate vectors on this straight line. Nothing else can be generated by multiplying it by the vector x. And this is exactly what it means to have a rank 1. Rank 1 means that although the vector is sitting in R2, meaning that it has two components, really it's a one-dimensional thing. That's what this one-dimensional line tells me. On the other hand, if this matrix A had rank 2, then that would tell me that I should be able to generate everything in R2, because it would mean that there are two independent vectors that I could generate, and I know that in R2, using two independent vectors, I can generate anything, and so on. In this course, we will never get down to the details of how do I compute the rank and so on. We'll work mostly with the sort of the idea of what a rank is. And the idea that I want you to keep in mind is rank tells you the richness. Higher rank means that you can get a lot more things out of this linear function. Lower rank means that you get less out of this linear function. In the next module, we're going to start talking about hedging and bring in an optimization problem. And there we'll notice that the rank of the matrix will tell me how many different payoffs I can hedge. Before we finish this module on matrices, there's one last concept, and that's of inverse. If I've got a matrix A, which is a square matrix, n by n, both the row index and the column index is the same, and the rank of the matrix is n, meaning that all the columns are linearly independent, all the rows are linearly independent, then this matrix is invertible. What does that mean? It means that there exists a matrix A inverse such that A inverse times A is the same as A times A inverse, and which is the same as identity. So this I, remember, was identity.